Understanding physics. This is another hard bit, this one. Lenz's law. Okay, what's Lenz's law? Well, an induced EMF will always oppose or tend to oppose the flux change producing it. Learn that word for word. And that is Lenz's law. And that fella there, Emil Lenz, came up with that. So what does that mean then? Well, consider this. I'm going to talk you through this step by step. Stay with me. At the end, it will be crystal clear. Imagine you've got a strong magnet, and imagine you've got a coil which has lots and lots of turns, and the coil is connected to a bulb. And basically, you shove the magnet inside the coil, and while the magnet is moving, the bulb lights up. Okay, so first of all, why does the bulb light up? We push the magnet inside the coil, the bulb lights up. Why? Well, while the magnet is moving, there's a flux change. Yeah, the amount of flux in the coil is changing. So we've got d psi dt, we've got a change in flux over time. Or you could say that the coil is cutting flux. If you imagine flux lines coming out of the magnet being cut by these copper wires. Okay, now Faraday's law tells us that we're going to get an EMF induced, and that EMF will be proportional to the rate of change of flux. So how quickly the flux is changing, or how much flux we cut every second, the rate of flux cutting, if you like. So Faraday's law tells us that we get a voltage, an EMF, proportional to, and I've said dn psi dt, so the rate of change of flux linkage, because it's a coil. So we've got n turns. I mean, you could say n d psi dt or dn psi dt. It's the rate of change of flux linkage. And as we've got a complete circuit with the bulb, we've got a voltage, and we have a circuit, so we can get a current. So a current will also be induced, and the bulb will light up. As long as the magnet is moving, the bulb will light up. Now, where does the energy come from to light the bulb? I mean, it can't come from the coil. It's just a piece of wire. Where does the energy come from to light the bulb? Well, where does the energy come from? Well, it comes from the person who is moving the magnet. The person who's got hold of the magnet, pushing it inside the coil. And that person is doing work. They have to do work, because that's where the energy comes from. It comes from their muscles. Okay, so they must have to need a force to push the magnet in, because they have to do work. Something has to work against them. There must be a force trying to stop them push the magnet in. Okay, so something is trying to stop them push the magnet in. There is an opposing force acting against them. Yes. Why? What is this force I'm talking about? Well, the induced EMF that we talked about on the last slide produces a current, and the current is flowing in the coil. Now, what happens when a current flows in a coil is you get a magnetic field. So this coil will produce a magnetic field. Yeah, the current flowing in the coil. So now we've got two magnetic fields. We've got the magnetic field of the permanent magnet, the bar magnet, and we've got the magnetic field produced by the coil. And those two fields will repel each other. They will oppose each other in such a way that they will try and stop the magnet being pushed in. Okay, look on the diagram. That left end of the coil will become a north, because it's saying to the magnet, no, I don't want you to come in, go away. It is opposing it, trying to stop it. Okay, what happens when we move the bar magnet out of the coil? Well, what happens when we move the bar magnet out of the coil is a similar thing. Now, the person will have to do work. Why will they have to do work? Because the energy to light the light bulb has to come from somewhere, and it has to come from the person moving the magnet. So what will happen this time is that the coil will say, "Oi, where are you going? Come back over here," and it will try to stop you from pulling the magnet out by becoming a south pole. Okay? So basically what's happening is that the EMF is trying to stop the magnet moving. It is trying to oppose, to go against the motion which is producing it. And that is Lenz's law. To make the person moving the magnet do work, the EMF will oppose the motion by producing a current, which produces a magnetic field, which tries to stop the motion of the magnet. It's a bit like friction. Friction always acts against, opposite to the direction that you're moving in. It always opposes motion. Similar to this. Okay. What if there was no circuit? Okay. Would you still get an EMF induced? And would it still oppose the motion of the bar magnet? And the answer is, well, would you get an EMF? Yes, you would. You would still get that voltage, okay? Would it oppose the motion of the bar magnet? And the answer is no. Why not? Because you wouldn't be able to have a current, because you haven't got a circuit now, so there'd be no current, so there'd be no opposition to the motion. What you'd actually find is if you were moving the magnet in and out of the coil, when the bulb is there, it would be quite hard to do. When the bulb wasn't there, then it would be much, much easier. You would have to do a lot less work. You're still getting the EMF induced, but because you can't have a current, the EMF won't be able to oppose the motion. That's why we say will oppose or tend to oppose. Yeah, it would like to oppose it, but it can't because there's no current. Yeah. As there is no circuit, however, a current won't flow, so the coil cannot produce a magnetic field to oppose the motion. So an induced EMF will always oppose or tend to oppose the flux change producing it. Now why? And it's basically conservation of energy, because the energy has to come from somewhere, and it comes from the thing which is actually making the magnet move. Another way of thinking about it, to cut flux you have to do work. Yes? To cut flux you've got to do work. If you look at this photo, this is a bicycle dynamo, and that produces electricity to make the light bulb work. Well, the point is that to make the dynamo go round, you've got to do work. If you've ever had one of these things and you're driving along on your push bike, when it's not connected, it's quite easy. When it is connected, you noticeably have to pedal harder to travel at the same speed, because you have to do more work, because the energy to light the light bulb has to come from somewhere. What I'd like to do now is to have a look at some typical exam questions. Okay, I think there's 3 of them that we're going to look at. And this is the first one. Hopefully this will have been demonstrated to you in your physics lessons. So a bar magnet is dropped through a plastic tube and then through a copper tube. Now use the laws of electromagnetism to explain why it takes much longer to fall through the copper tube. Now, I suggest you pause the video and have a go at this question by yourself. I'll show you the answer in 3, 2, 1. Okay, and this is my answer. So, as the magnet falls through the copper tube, the walls of the tube cut flux. Yeah, the copper, it's copper and it's cutting flux. Yeah, from Faraday's law, when we say the laws of electromagnetism, we're talking Faraday's law and Lenz's law. So from Faraday's law, an EMF will be induced in the copper proportional to the rate of change of flux. So you mention Faraday's law and say what it is as well. Yeah, so from Faraday's law, you're going to get an EMF proportional to d psi dt. And this EMF will produce a current in the tube because it's a tube, because it's a circle. So you get current sloshing around in a circle inside the copper. And that current will produce a magnetic field. Now, from Lenz's law, this field will oppose the flux change causing it by opposing the motion of the bar magnet. So the induced EMF will produce a current which will produce a field which will try to slow down the magnet because the two magnetic fields will oppose each other. Yes? So again, it's a bit like friction. Yes? The induced field will oppose the motion of the magnet. In plastic isn't a conductor, so you're not going to get any EMF, never mind a current. This kind of question is 6 marks, by the way. Yes, loads of marks. With Lenz's law, you're probably not going to get, well, you won't get anything mathematical. It will be showing your understanding. Mention Faraday's law, say what it is. Mention Lenz's law, say what it is, and then explain how it applies to this particular situation. Here's another one. Hopefully this has been demonstrated to you. It's the floating ring. So this aluminium ring is floating. It kind of bobs up and down and it rattles a little bit as well. This aluminium ring floating on this retort stand. You've got an AC power supply, won't work with DC. You've got a coil, you've got an iron retort stand and this floating ring. And it says use the laws of electromagnetism to explain why the aluminium ring floats as shown. And again, there'll be about 6 marks for this. Pause the video, have a go yourself. My answer is in 3, 2, 1. So, an AC power supply. The current is constantly changing. So we're going to get a constantly changing magnetic field. Yes, my magnetic field, the flux will be sinusoidal, sloshing backwards and forwards, a constantly changing magnetic field. And this alternating flux will flow through the iron retort stand because iron has a high permeability. Yeah, so the flux will tend to stay inside the iron. So you've got flux sloshing up and down through the iron retort stand and through the aluminium ring. From Faraday's law, we're going to get an alternating EMF induced in the ring. And because it's a ring, we're going to get an alternating current induced in the ring. One interesting thing, if you actually hold the ring and try pushing it down, it gets very, very hot because there's so much current sloshing around in it. There's a lot of I squared R going on. It produces a lot of heat. Yes. But anyway, so you've got alternating current sloshing around in the ring. That's going to produce a magnetic field. And from Lenz's law, the induced field will oppose the original field. So the two fields will be opposite to each other. And that will produce an upward force on the ring. And the ring will float. It'll be in equilibrium when the upward force due to the magnetic force will be equal and opposite to its weight. If you're interested, I'm sure you've heard of maglev trains, yeah, magnetic levitation. And this is kind of the same principle on how these trains can actually float. And so there's very, very little friction as they move along. Last one, and you should know this one as well. Now what's happening here, we're dropping a magnet through a coil and we're looking at the voltage, the EMF. You can either do it with an oscilloscope, like a storage oscilloscope, or with a data logger. A magnet is dropped through a coil. The coil is connected to a data logger that records the EMF, the voltage, induced against time. Use the laws of electromagnetism to explain the graph of voltage against time obtained. Okay, So again, the laws of electromagnetism. We're talking Faraday's law. We're talking Lenz's law. Pause the video, have a go. And my answer is in 3, 2, 1. From Faraday's law, the induced EMF is proportional to the rate of change of flux. The EMF induced at B, now you see there's two parts of the graph, there's A and B. Now the EMF induced at B is bigger because the magnet is moving faster. Yeah, it's been accelerating due to gravity, so the magnet is moving faster, so d psi dt is bigger, so the EMF at B is bigger. Now, the EMF at A and B, they're in opposite directions, they're at opposite signs. Why? Because at A, the magnet is coming into the coil, so the EMF is trying to oppose this. It's saying, no, go away. At B, the magnet is leaving the coil, so the EMF again is trying to oppose this. So from Lenz's law, the EMF opposes, first of all, the magnet coming in, and then the magnet leaving. And that's why the EMF at A and B have opposite signs. If one's positive, then the other's negative. A little summary just to finish. The laws of electromagnetism. If it says that, Faraday's law, Lenz's law, say what they are. Learn them. Yes, say what they are. You have to do work to cut flux. To turn a generator, you have to do work. Why? It's conservation of energy. The energy has to come from somewhere. So to make you do work, the induced EMF opposes the motion creating it. So it will try and stop the field from changing. Yes, you've got to do work to cut flux. And it does it by producing a current, which produces a field, which opposes the change in the original field. So I hope that helps. If there's any particular bits of physics that you want me to do a video on, like you think it's a hard bit, let me know in the comments and I'll be happy to do that. So bye for now.